Hello everyone, I am Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about ferroelectricity. In the previous lectures, under the head Electric and Magnetic Materials, we have seen the introduction to dielectrics, the types of polarization and internal field in solids, as well as Clausius-Mosatti equation. And today we are going to discuss about photoelectricity. So for the basic things, you can always refer to these videos so that you will have a continuity for ferroelectricity. So let us see the brief outline of this topic, ferroelectricity. First, we'll see the definition. What is ferroelectricity? Then we'll discuss about the different types of materials. And then comes the properties of ferromagnetic materials, that is piezoelectricity and pyroelectricity in detail. And then finally, we are going to discuss about a very important property, which is dielectric hysteresis. So coming to the definition of ferroelectricity, some materials possess spontaneous polarization even when electric field is not applied. Spontaneous polarization even when electric field is not applied. This is very important. In the previous lectures, as I told you, we have discussed in detail about polarization and different types of polarization. So the materials which exhibit spontaneous polarization even without the application of electric field, because in nature there are some materials which get polarized on application of an electric field, but these ferromagnetic materials, ferroelectric materials, they show spontaneous polarization even in the absence of an electric field. So how they are exhibiting these spontaneous polarization is they have acquired electric dipole moment. So they have a dipole moment even when no field is applied. So what is this dipole moment? So what is a dipole we'll see, and then we'll see what is dipole moment. So what is a dipole? Two equal, these are two equal charges but opposite in charge. They are separated by a distance r, say. So, two equal and opposite charges separated by a distance form a dipole. This is a dipole. Now, when we have a dipole, what is the formula to find the dipole moment? The dipole moment is always denoted by mu, and mu is equal to charge multiplied by the distance between the two charges. So mu, the dipole moment, is given by mu is equal to q into r. So they are having this acquired dipole moment even when no field is applied. So this type of materials we are calling as ferroelectric materials, and these exhibiting this property or this phenomena, we call it as ferroelectricity. Now, when it comes to the ferroelectric materials, there are three main types of crystal structures. In ferromagnetic materials, we have three main types of crystal structures. So, the first one is Rochelle crystal or salt structure, which is also called as sodium potassium nitrate. So, Rochelle salt structure, the name is sodium potassium tartrate. So, and the formula we see how we represent it is NaKC4H4O6 4H2O. And the second one is perovskite group. This consists of titanates and neobates. And the example for that is barium titanate. Barium titanate is another example for a ferroelectric structure. It is denoted by BaTiO3. And then the third one is dihydrogen phosphates and arsenates. Dihydrogen phosphates and arsenates, KH2PO4. So these are the three main types of crystal structures we see in ferroelectric materials. Now there are some other examples like ammonium dihydrogen phosphate, NH4H2PO4, and also lithium niobate, that is LiNbO3, and also we have potassium niobate, KNbO3. So these are other examples for ferroelectric materials. Now coming to the properties of ferromagnetic materials. So we have seen that they possess spontaneous polarization below a certain temperature. So we will discuss about this temperature in the future slides. So what happens here is, below a certain temperature, all these ferromagnetic materials, electric materials, they possess spontaneous polarization. And what happens as the temperature increases? The spontaneous polarization decreases. So if the temperature increases, the polarization decreases, and at a particular temperature, this spontaneous polarization vanishes. Means they do not exhibit this polarization anymore at a particular temperature. And this temperature we call it as Curie temperature. This temperature is very important. Sometimes we denote it by Tc or theta C. So means below the Curie temperature, the ferromagnetic materials exhibit spontaneous polarization. But as we increase the temperature and as it crosses the Curie temperature, the spontaneous polarization vanishes. So it is defined as the temperature at which a ferroelectric material gets converted into a paraelectric material. Ferroelectric material is getting converted into a paraelectric material. At what temperature? At Curie temperature. Because below Curie temperature, they are exhibiting spontaneous polarization, and that is ferroelectric property. And at Curie temperature, this property vanishes, and then they will behave like paraelectric materials. So let us understand it with the help of the graph. Below Curie temperature, the dielectric material possesses ferroelectric property. So now let us see the graph. So this is what we are plotting. We are taking the temperature along the x-axis, and we are taking the polarization or the dielectric constant we have taken along the y-axis. Now at a particular temperature, we are talking about Tc. Below Tc, the Curie temperature, the material will exhibit spontaneous polarization. But as the temperature increases above Tc, the spontaneous polarization gradually decreases and it vanishes. So as the temperature increases, the dielectric constant reduces after Tc. So the dielectric constant is reduced. So this is the graph which we see for variation of dielectric constant with temperature. Now we are going to see the Curie-Weiss law. Curie is the name of the scientist. So Curie-Weiss law. So epsilon R is equal to C upon T minus Tc. So this is the relation he gave for dielectric constant and Curie temperature. What is epsilon R? It is the dielectric constant, and C is the Curie constant. Epsilon R and C both are constants, but this is the dielectric constant, depends upon the material, and C is the Curie constant. And T here is the absolute temperature, which is always measured in degree Kelvin, and Tc here, T suffix C represents the Curie temperature. Now the ferroelectrics exhibit the properties called piezoelectricity and pyroelectricity. So these are two important properties, piezo and pyro. So what is piezoelectricity? This means when mechanical stress is applied to ferroelectric materials, then opposite charges are formed on the surface of the crystal, generating electricity. Means if you are taking a ferroelectric material and you will apply stress on both the sides, you will subject this to stress, then what happens? Opposite charges are developed on either side. So whenever there are opposite charges that are developed, there will be a potential difference, then there will be a flow of current that generates electricity. So this word piezo is coming from the Greek. So in Greek, piezo means pressure. So whenever we are subjecting it to some pressure, then what is happening? Opposite charges are being developed on the surfaces of the crystal, and because of that electricity is generated. So this property of generation of electricity when a ferroelectric material is subjected to mechanical stress, we call it as piezoelectricity. Then the second one is pyroelectricity. What is pyro here? Pyro is again a Greek word which means heat. It means the change of a spontaneous polarization by application of temperature. So when we are applying temperature or when we are heating the ferromagnetic material, its polarization will vary. So that property we are calling it as pyroelectricity, and the generation of electricity due to this we call it as pyroelectricity. Now another property we see here is dielectric hysteresis. What is dielectric hysteresis? It is the lagging of polarization behind the electric field. So what we see in some materials is as we increase the electric field, there are more and more dipoles that are formed. There will be polarization. But what we see here is the polarization is always lagging behind the electric field, and that we call it as dielectric hysteresis. So the area of the loop represents the dielectric loss. So by drawing this hysteresis loop, we can calculate the area of the loop and find out the dielectric loss in that particular material. Now let us discuss in detail about these properties. So the first one we have seen is piezoelectric effect. Some say piezo or piezo. So the development of electrical charges and electrical polarization when subjected to stress. So what is important? We take a ferromagnetic material and we subject it to stress. So then what happens? There are development of electrical charges. Charges are being developed on the surface. So we are calling it as piezoelectric effect. And this phenomenon was discovered by Curie brothers in the year 1880. So crystals like quartz, tourmaline and rochelle, when subjected to compression or tension, develop opposite charges. There are two different types of stress. Either we elongate it or we compress it. Any kind of stress these ferroelectric materials are subjected to, the opposite charges are formed on the surface, and because of which there is electricity. And we are calling the effect as the piezoelectric effect, and the electricity that is generated in this manner, we are calling it as piezoelectricity. So the materials also exhibit inverse piezoelectric effect. What is inverse piezoelectric effect? So when this material is subjected to electric field, they get strained. They get strained means what happens? Their dimensions get changed. They may either expand or contract. So that is why we are calling it as inverse. In piezoelectric, what we have seen, we are subjecting it to stress and the result is electricity. Now we are applying an electric field. In inverse, we are applying an electric field and the result is there will be a strain, there will be a change in the dimensions. Either the crystal may get expanded or contracts. And now if you see, all ferroelectric materials exhibit this piezoelectric property. So if you are taking a ferroelectric material, they all exhibit this piezoelectric behavior. But all piezoelectric materials need not be ferroelectric. This is one thing we have to remember. So if you are taking any ferroelectric material, it is piezoelectric. But all piezoelectric materials need not exhibit the properties of ferroelectricity. Example, we take here barium titanate. This exhibits both ferro and piezoelectricity. So it is a ferroelectric material, it exhibits piezoelectricity. But when we take quartz, it is only piezoelectric and it is not exhibiting the property of ferroelectricity. Now, if you are seeing the piezoelectricity in different quartz crystals, quartz is nothing but silicon dioxide, which we write it as SiO2. And the atoms are arranged in the form of an hexagon. So, the arrangement of atoms, different crystals have different arrangement of atoms. So, here when we are taking a quartz crystal, the arrangement of atoms is in the form of a hexagon. And it will have three axes, the x-axis, the y-axis and the z-axis. X-axis is known as the electrical axis, y-axis is known as the mechanical axis and z-axis is known as the optical axis. So let us see it in the figure also. Now when electric stress is not applied, all the charges get balanced. So the net polarization is 0. But when we are applying an external stress, the balance is getting disturbed and the crystal gets polarized. So when it gets polarized, electric charges are developed on the faces. So whatever we have discussed, how a ferroelectric material is exhibiting the electrical properties on subjecting to stress. So when the stress is not applied, what is happening? All the charges are getting balanced. So the net polarization is 0. But whenever we are subjecting it to external stress, this balance gets disturbed and the crystal gets polarized. So whenever there is polarization means the separation of charges. So the opposite charges are developed on the surfaces, opposite faces, and we have the electric charges. So this is the figure we see here. In the quartz crystal, we said that the atoms are arranged in a hexagon fashion. So in all the corners, this is the hexagon which has 6 sides. So 1, 2, 3, 4, 5, 6 atoms at all the corners. So when no stress is applied, all these are balanced. There is no polarization. So no electric charges. But now, when we are subjecting this to tension, means I apply force on both the sides. We are subjecting it to tension. Then what happens? The polarization starts. So there will be polarization and because of which the charges are developed on the surface of the crystal. The same thing you see when it is compressed. On subjecting the crystal to compression, means we will try to compress it on both the sides. So when you are compressing again, there will be development of charges. So here you see the positive charges and the negative charges. So anyway, when you are trying to expand it or compress it, there will be polarization due to which the development of charges are happening on the surfaces of the crystal. And in case of inverse piezoelectric effect, if the quartz crystal is subjected to alternating electric field, it will either expand or contract. And this also undergoes vibration. So whenever we are subjecting it to an alternate electric field, so it will either expand or contract. Now, what are the applications of these piezoelectric materials? If the frequency of vibration is equal to the ultrasonic frequency, then ultrasonic waves are produced. Means these piezoelectric materials can be used in the production of ultrasonic waves. So what are ultrasonic waves whose frequency lies in the ultrasonic region? So now when we are taking a quartz crystal and then we apply the inverse piezoelectric effect that gives rise to vibrations. And when the crystal is vibrating and if the frequency of the vibration is equal to the ultrasonic frequency, then ultrasonic waves are produced. So we are using a quartz oscillator most of the times to produce ultrasonic waves. Then Rochelle salt, a dielectric material, is used in gramophones. Gramophones which were used in earlier days, they have used this Rochelle salt. And earphones, hearing aids, microphones, all of them are using this particular material. Then barium titanate, lead zirconate, lead titanate, they are used in high voltage generation. Because we have seen when they are subjected to stress, they produce electricity. So these are used for high voltage generation. Now, a transducer, it can be used in transducer also. A transducer is a device which converts one form of energy to another. And piezoelectric effect can be used in transducers to convert force, pressure and strain into electrical voltages. So with the help of this, we are converting one type of energy into another type of energy. And also we have acceleration transducers which are used to measure the acceleration. The transducers which can measure acceleration, we are calling them as acceleration transducers. Then piezoelectric crystals are also used to produce radio frequency waves for broadcasting. So wherever we are using radio frequency, RF range, there also we are using piezoelectric crystals. Then we have quartz watches to maintain accurate time. So watches made up of quartz are very famous. They are well known to maintain accurate time. Now coming to the next property, that is pyroelectricity. So what is pyroelectricity? If you first talk about the change or the effect, it is a change in spontaneous polarization when the temperature of the specimen is changed. Means when you are heating it and the temperature changes, there will be a change in polarization. And this effect we are calling it as pyroelectric effect. So we will understand how these crystals are exhibiting this pyroelectric property. So many piezoelectric crystals such as tourmaline have the tendency to exhibit internal electrical polarization as a response to temperature changes. So an electric field develops in a pyroelectric crystal as a result of temperature change. So when the temperature changes, the electric field is developed. That is why we are calling it as pyro. So it requires the presence of permanent electric dipoles whose magnitude is not affected here by other effects but only due to the temperature. Its magnitude is affected as a result of the temperature changes. Then it is possible to detect a change of 10 power minus 16 coulomb with a suitable electrometer. We use electrometers to detect this change in electricity up to the range of 10 power minus 16 coulombs when the temperature changes are as small as 10 power minus 6. So we can measure such changes in electricity or the charges by varying the temperature. Now coming to the applications of pyroelectricity. So pyroelectric materials like barium titanium oxide BaTiO3 and LiNiBO3, they are used to make very good infrared detectors which can operate at room temperature. Also, we have materials as TGS and NaNO2 and ceramics, which are used in the construction of pyroelectric image tubes. So, pyroelectric image tubes are also made using this materials. So, they are also used in burglar alarms, which detect the thermal radiation from the human body, because they are temperature dependent. So when the temperature varies, the polarization varies. So in burglar alarms, whenever there is a human body that is there, the radiation that is emitted, the thermal radiation can be detected and the burglary can be prevented. Now coming to the next property, that is dielectric hysteresis. What is dielectric hysteresis? First we will understand this. It is a property of the lagging of polarization behind the applied electric field. So whenever we are applying an electric field to a ferroelectric material, the polarization is lagging, means it is not matching with each other. So what is this lag? How is this lag? We will try to understand it with the help of the figure. And the area of the loop represents the dielectric loss. So whenever you have to measure the dielectric loss in a given material, this dielectric or the hysteresis loop helps us in calculating the dielectric loss. So what we are doing here is, we are taking the electric field, the applied electric field along the x-axis and the polarization along the y-axis. P represents the polarization. So what we do here is, we will keep on increasing the electric field. So as the electric field increases, this is the origin, so the polarization also increases. You can see the arrow here. So as the electric field increases, the polarization also increases and it reaches a saturation point. P sat is nothing but saturation. So the polarization becomes saturated at this electric field. Saturation means even after this point, even if you apply the electric field, there is no further increase in polarization. Means all the dipoles are aligned and there is no further chance left for polarization. So we call it as the saturation point. Now what we have seen here is, as the electric field is applied, polarization rapidly increases and it reaches a point called the saturation polarization, which is a constant. Now if the electric field is made zero, means I have applied the electric field and the material is getting polarized and it is reaching the saturation. Once it reaches the saturation point, we try to withdraw the electric field. So if the electric field is withdrawn, what we expect is, the same way it has increased, we will imagine that it will reach zero. When the electric field is zero, the polarization also has to be zero. That is what will be our expectation. But what we observe here is, it will not reach the original point O. As we are withdrawing the field, this is how the polarization is varying. And when the electric field is zero, the polarization is not zero. It is PR. So PR here represents the remnant or the remained polarization. Even when the electric field is zero, the polarization is not zero. There is some remnant polarization or the polarization which still remained in the material. So we are calling it as PR. So P saturation is the saturation point at which the polarization is saturated or the peak point. After that, we are going to withdraw the electric field. We are trying to make it zero slowly. But what we are observing is, at zero applied field, the polarization is not zero, but it is PR. This PR we are calling it as remnant or remaining polarization. Now to destroy this PR means to bring this PR to zero. To remove this, what we have to do is, we have to apply a negative electric field. Okay, and then PR will become 0. So what do you mean by negative electric field? So we have taken plus E along the positive x-axis, we will take minus E along the negative x. So after the PR, what we are going to do is we are going to apply negative electric field. So this is what we are applying. So slowly, at a particular point, the electric field becomes 0. So the point at which PR becomes 0, we are calling it as negative coercive electric field, and it is denoted by minus EC. So you see here, this is minus EC. What is this called? This is negative coercive electric field, because we have applied negative electric field and we are calling it as coercive electric field because at this point PR becomes 0. Now if we are further increasing the electric field in the negative direction, we are further going in the negative direction, then what happens here? It reaches a point minus PS, which is known as negative saturation polarization. Again, it goes to negative saturation. I'll say this is minus PSAT. That is a negative saturation polarization. And if this negative field is increased back to 0, the negative saturation minus PS will not go to the point O, but again it creates a new path at the point minus PR. So what we did here, if you are seeing the loop, first we have applied the electric field. So the polarization increases and it has become a saturation. So once it reaches the saturation point, what we did, we started withdrawing the electric field and we have expected that it will go to 0, but it did not. What happened is, it is going along a different path. And in this path, at the point O, that means when electric field is equal to 0, we are still having some polarization, which we are calling it as remnant polarization. So to bring this PR to 0, what we are doing is, we are applying a negative electric field. So as we increase the negative electric field, this PR slowly decreases, and at a particular point or at a particular electric field, which we call it as a negative coercive electric field, the PR becomes 0. So even after PR becomes 0, when we further increase the negative electric field, it is going along this direction negative, and it is again reaching a saturation point, which we call it as minus PSAT. After that, again, we try to bring it to 0. We are trying to reduce the electric field, negative field also. Again, it is not reaching 0, but it reaches a point which we call it as minus PR. Here also, it is reaching a point called minus PR. This minus PR, we are calling it as negative remnant polarization. And now to destroy this PR, we will apply a positive electric field. So when we are applying a positive electric field, so this is how it goes. So to destroy minus PR, we are applying a positive electric field, and this field EC is called the positive coercive field. So here at this point where it becomes 0, we will call it as positive coercive field EC. So at last, the increase in electric field leads to the reach of positive saturation polarization, and this is a complete cycle. We call it as a cyclic process. So even after reaching the point EC, we are applying the field. It again goes back to the saturation point. And this is one complete cycle, we say. This is one complete cycle. We have increased the electric field. We have withdrawn the field. To bring PR to 0, we have applied negative field, brought it to the negative saturation point, and again we have decreased the negative field, and here it is becoming minus PR, and at one particular point of positive electric field, we call it as the coercive electric field, it becomes 0, and then again it increases, and this is one complete cycle. And in the above mechanism, what we have seen, the polarization started at the point O, but it is not reaching back to that point. So what is the meaning of this? the polarization always lags behind the electric field. So if while increasing it has gone like this, and while decreasing if it has come back like this, means they are not lagging behind. They are in phase, I can say. There is no lag. But here, at no point it is reaching back to O. So there is always a lag. The polarization lags behind the electric field, and this we call it as dielectric hysteresis. So we'll now see the applications of the ferromagnetic, the electric materials. So ferroelectrics have high dielectric constant epsilon R. So epsilon R is the dielectric constant. They have very high dielectric constant. That is why they are used in small sized capacitors to produce large capacitance. So they can produce large capacitance. And also because they satisfy this dielectric hysteresis property, they can be used as memory devices in computers. Then piezoelectric transducers are also used to produce and detect sound waves. And they are also used to detect infrared radiation. So for more details regarding this topic, you can refer to Concepts of Physics by H.C. Verma, and you can also refer to Introduction to Electrodynamics by J. Griffiths, and Unified Physics, Electricity and Magnetism and Electronics by Dr. S.L. Gupta. So thank you, and see you again in my next lecture.
Like, share and subscribe. Hit the bell icon for more updates.